Hey everybody, this video lesson is on solubility equilibrium, or the idea of KSP. It's an equilibrium constant for dissolving. You can find a copy of these blank notes on our Schoology page. It might be a good idea to have these notes because the practice problem, the practice FRQ that I'm going to do, can be uploaded into Notability and then you can do it along with me. There's a small section in the textbook about solubility product. It's chapter 17.4 on page 722. And as I mentioned, this is an equilibrium concept. Equilibrium expressions can be expressed in three different ways: Kc for concentration, Kp for pressure, or Ksp for something that is dissolving. Now if we generate a solubility expression for an ionic substance, we'll call it AB, the substance AB is breaking down into A plus and B minus, both of which are aqueous. Now the equilibrium expression, remember, is the concentration of products over the concentration of reactants. And in this case, it's the concentration of A plus and B minus. But the denominator in this case, because it's a solid, does not happen to be included in the equilibrium expression. Remember, when you're doing equilibrium expressions, only aqueous and gaseous species are in the equilibrium expression. So in the reactants part of the equilibrium expression for KSP, we have just a 1 in the denominator, and oftentimes we don't even write the 1. So to clean it up, KSP is equal to the concentration of the A ions times the concentration of the B ions over 1, or just that's it. And don't forget, if either of these products have a stoichiometric coefficient in front of them, then that's going to be expressed as an exponent in the equilibrium expression. Now a few general comments on the equilibrium expression for solubility, or KSP. First of all, it's assumed that the solution is going to be at its saturated state. Remember, the concept of saturation means that it has the maximum amount of ions that could be dissolved in the amount of solvent that you see in front of you. In fact, you might even see a little bit of undissolved precipitate sitting at the bottom. It's the solid that cannot be dissolved anymore because the solution has taken the maximum amount of ions that it could possibly take. The second thing I want to say is that all of these are temperature dependent. Like all equilibrium constants are temperature dependent, solubility likewise is temperature dependent. So almost always, equilibrium constants for solubility are expressed at 25 degrees Celsius, or standard state conditions. Now a couple of other general observations about KSP. If the number for KSP is much, much larger than 1, then we consider that a highly soluble substance. And think about that in terms of the math. If you take some AB solid and you put it in and you get lots of ions of A and lots of ions of B dissolving into the solution, then these two numbers are going to multiply together to be a very, very large number. And if you have a high concentration of A and B in solution after it dissolves, then you have a very high KSP, which means it's very soluble. Now on the other hand, if KSP is much, much smaller than 1, then we would consider that very insoluble. So take the same example, AB gets put in only a couple molecules compared to the overall amount. Maybe you put 10 grams of AB solid in and you get a couple molecules of A and a couple molecules of B ionizing in the solution, then A times B is not going to be very large, and that number multiplied together results in a very, very small number. We're talking about like times 10 to the negative 5th or 10 to the negative 10th. Then you'd consider that substance to be very insoluble. Here's a real example of a substance that has a very, very low solubility. BaSO4, when dropped into the water, only ionizes a very, very small amount. Now you get some Ba ions in solution and some SO4 minus ions in solution. And so the expression for KSP is Ba plus 2 concentration times SO4 minus 2. And when you multiply the Ba ions times the SO4 ions in solution at 25 degrees Celsius, the concentration is not very large. In fact, you have such a small quantity that the concentrations multiplied together give you 1.1 times 10 to the negative 10th. Now remember, it's an equilibrium constant, so it's a unitless value, but it's very, very small, so you can say that this substance is fairly insoluble. Now I'm going to take you through an FRQ type situation that involves KSP specific information. So here's what we got. We have 100 milliliters of solution, and it's saturated with MgF2. We added 0.5 grams of the solid into the 100 milliliters of water at 25 degrees Celsius, and it dissolved until no more solid dissolves. Now we're going to assume that the MgF2 particles themselves do not contribute to the overall volume, so we can basically say that the volume of the liquid is the volume of the solution overall. Now the saturated solution is analyzed and determined that the F minus in the solution is 2.4 times 10 to the negative third molar. Now we're going to need that information, but not right away. Let's answer this first question. Write out the chemical equation for the dissolving of the solid MgF2 in water. And when I do that, I start with the MgF2 and I break it up into its individual ions. So you've got one Mg ion and two F minus ions. Now originally the 2 was a subscript behind it, and that's the case when you have an ionic solid like MgF2. But when it's dissolved, the 2 comes out in front and becomes a stoichiometric coefficient. I have 2 moles of F minus ions. I should probably also include the states of matter, but it's assumed that it's dissolving, so they are in their aqueous state. Now for number 2, calculate the number of moles of MgF2 that got dissolved. Now we're going to utilize the concentration of the F minus ions that it talked about in that last sentence, and able to do some stoichiometry to calculate the moles of MgF2 that are dissolved. Because even though we put in 0.5 grams of the MgF2, we didn't dissolve all of it. So I'm trying to calculate of this 0.50 grams, how much of it did get dissolved. So the first thing I'm going to do is I'm going to take the 100 milliliters of solution and multiply it by its molarity, 2.4 times 10 to the negative third moles over 1 liter. And then I'm going to use the stoichiometric coefficients from the balanced chemical reaction up above in order to figure out how many moles of the MgF2 got dissolved. So there's 2 moles of F minus for every 1 mole of MgF2. And when I put that into my calculator, I get 1.2 times 10 to the negative fourth moles of MgF2 that got dissolved. The most common mistake I see here is that students use 1 mole of F minus down here, but you need to use the stoichiometric coefficients. This is the mole to mole conversion from moles of F minus to moles of the MgF2. Reading through number 3 now, it asks to determine the value of the KSP for MgF2 at 25 degrees Celsius. So let's write out the expression. KSP is equal to the Mg concentration times the F minus concentration, but that's squared, remember, because the stoichiometric coefficient is a 2. Now I know the F minus concentration because it's given to me up above, 2.4 times 10 to the negative third molar. But what I don't have is the Mg2 plus concentration. But I can use the answer from part 2 to figure out the answer to the Mg2 plus situation that I am encountering now. Because in the balanced chemical reaction from up above, 1 mole of MgF2 is equal to 1 mole of Mg2 plus. So I calculated 1.2 moles, 1.2 times 10 to the negative fourth moles of MgF2. So that means that I have 1.2 times 10 to the negative fourth moles of Mg2 plus ions as well. But remember, we're looking at concentration, not number of moles. So in the solution of 100 milliliters, or 0.1 liters, I have 1.2 times 10 to the negative third molar Mg2 plus ions. Again, the reason I can't just take this number of moles and plug it in here is because KSP is not moles times moles, it's molarity times molarity. And I need to take the number of moles from part 2 to figure out the moles of Mg2 plus and then calculate the molarity. Now I can take this number and plug it in. So I just duplicate that number and I drag it over here and I multiply 1.2 times 10 to the negative third times 2.4 times 10 to the negative third. But let's not forget that it's a squared term here. Before I multiply, I need to square this. And once I punch that in my calculator, I take 1.2 times 10 to the negative third times 2.4 times 10 to the negative third squared, and I get 6.9 times 10 to the negative ninth, and that is equal to the KSP of the MgF2. But wait, there's more to this problem. So as I read through this problem, I have 500 milliliters of total solution that holds both calcium ions and barium ions, and they're both 0.1 molar. And so I've drawn a little beaker down here to show what's going on. 500 milliliter beaker with 0.1 molar calcium and 0.1 molar barium ions. It says the student intends to separate these ions by adding 0.2 molar NaF solution, 1 drop at a time, from a burette. Now the NaF is going to mix and is going to precipitate out either the calcium fluoride or the barium fluoride. Now the first question is, which salt will precipitate first, the calcium fluoride or barium fluoride, based on the KSP values? Now remember, I said the smaller the number, the less soluble. So comparing these two numbers, the CaF2 will precipitate out first because it is the smaller the KSP values. And again, I know that by comparing the two values of KSP of the two fluorides, the one that's smaller, or the one that's times 10 to the negative 11th, is going to precipitate first. Now it says for part B2 and part B3, assume the addition of the NaF solution does not significantly affect the total volume of the liquid in the beaker. Again, by making that assumption, the 500 total milliliter volume of the beaker is going to remain 500 throughout the duration of this titration. So we don't need to worry about the volume of the NaF being added contributing to the total volume. So let's read through part 2. It says, calculate the minimum concentration of F- ions necessary to begin or to initiate the precipitation of the salt selected in part B1, or the calcium fluoride. So I quick jotted down the KSP expression, calcium ions times the fluoride ions, that's to the second power because it's CaF2, is equal to the KSP 3.5 times 10 to the negative 11th. Now we know the calcium ions began as a 0.1 molar solution, but we don't know what this is, but it's squared, and it's 3.5 times 10 to the negative 11th here. So now all we need to do is solve for x. The first thing we're going to do is divide by 0.10 on each side, and what I get is x squared is equal to 3.5 times 10 to the negative 10th. And you'd expect this to be some pretty easy math because dividing by 0.1 is the same as multiplying by 10. And so you just move the decimal point over 1 to the left. So it's just 10 to the negative 10th rather than 10 to the negative 11th. So the next thing I need to do is then take the square root on each side to isolate the x. So x is equal to the square root of 3.5 times 10 to the negative 10th. And I can easily do that in my calculator by taking square root of the second answer, and I get 1.87 or 1.9 times 10 to the negative 5th. And that's a molarity of the F- ions. Now with that information, the concentration of the F-, along with the original 500 milliliters, I can answer part 3. It says calculate the minimum volume of 0.2 molar NaF that must be added to this beaker in order to initiate the precipitation. Now, because we've established that Ca will precipitate first, I'm just going to cross out the Ba plus 2 because it's really non-essential in this problem. We're only working with the calcium plus 2. And now I can use some stoichiometry to calculate the volume. So start with the volume in liters, 0.500 liters of this solution, and I'm going to multiply it by the molarity of 1.9 times 10 to the negative 5th moles over 1 liter, and that's of the F- ions. Now I need a mole-to-mole ratio. We're trying to figure out the volume of the NaF that will precipitate, and so we need to use a balanced chemical reaction with these stoichiometric coefficients. And for every 1 mole of F-, I need 1 mole of NaF. And finally, I take the molarity of the concentrated NaF and I put that on the bottom. That's how many moles of NaF there are for every 1 liter. And I do a little solution stoichiometry. In summary, we started with 500 milliliters of solution, and we needed to add this concentration of ions to the solution in order to begin the precipitation. Well, the source of the F- ions is the NaF. So once I take the volume times the molarity of the F ions that we calculated up above in part 2, I can then use the mole-to-mole ratio of the titrant NaF in relationship to the Na plus and the F minus. The mole-to-mole ratio you want to use is for the titrant, not for the analyte. Most common mistake I see here is people do this for the CaF2, but we're trying to figure out the volume of the titrant, not the analyte. So 1 mole of F minus for every 1 mole of NaF, and then I finally use the concentration of the titrant, NaF, to figure out how many liters. And my final answer is 4.75 times 10 to the negative fifth liters. And this last question is more of an experimental design type question, but it says there are several ways to dissolve salts that have limited solubility. For example, the CaF2, which we precipitated out in the previous example. Describe one procedure to redissolve the precipitate form from part B, which we again decided was CaF2. Now, one thing you can do to dissolve more salts is add heat. Remember, we said how these equilibrium constants are all heat dependent, and the reason we do them at standard temperatures is because we want to establish a constant temperature so that the solubility constant is always based on that temperature. But increase the heat and you can dissolve more salt in the substance. Or you might need to lower the heat, because these are all basically guided by Le Chatelier's principle. If you have an endothermic salt, say for example CaF2 was endothermic, meaning you added heat in order to make it dissolve. If you add more heat, it's going to shift equilibrium further to the right. And so endothermic, add heat, it will shift equilibrium to the right to dissolve and make more Ca2 plus and 2F minus. But if it happens to be an exothermic salt, then in order to get it to dissolve, you want to cool it down, because removing the heat shifts equilibrium to the right, which would then allow more CaF2 to dissolve into the solution. So in summary, change the temperature depending on whether or not the heat of the solution is endothermic or exothermic. And that's one way in order to dissolve limited solubility salts. The second most common way to dissolve salts that have limited solubility is take the salt CaF2 and figure out, in a single displacement sort of situation, what is a metal that is more reactive than calcium on the activity series that could come in and kick out calcium, so that calcium is now ion, and then the mystery ion plus F is also aqueous. So one way to dissolve a salt that's not very dissolvable is introduce a cation in the form of a metal that is higher on the activity series that could kick out the calcium, and thus you dissolve the calcium fluoride by creating 3 aqueous ions in solution rather than a solid metal and a low solubility salt. In this case, I'd always pick lithium to do the job, because lithium is at the top of the activity series. And so lithium will come in and kick out calcium and become lithium fluoride aqueous, and then the calcium ions would then themselves become aqueous. And that would then dissolve the calcium fluoride solid, because the solid, let's think about it this way. The lithium comes in and kicks out the aqueous calcium ions, because there are some aqueous calcium ions, and then the solid calcium will come in and replace those aqueous ions that were in solution, and then those lithiums will continue to kick those out, and then more calcium will dissolve to kind of reestablish the concentration, and then those lithiums will kick that out, and then more calcium. Eventually, all the calcium fluoride will dissolve because all the lithium comes in and kicks it out, and that's how you establish a aqueous product situation from a limited solubility salt. Well, that takes care of this video lesson on solubility product. Thanks for watching.